December 3, 1944. The forests of the Hürtgen, Germany. Sergeant Klaus Reinhardt pressed his gloved hands against the breech of the 88mm KAWK-43 gun, its metal surface cold enough to burn exposed skin. Around him, the crew of Panzer 508, a Panther Ausf G, waited in tense silence as the order came down from their commander. Load armor-piercing. Prepare to engage. But Reinhardt did not move. Neither did his loader, Gefreiter Matthias Weber. The two-piece ammunition sat ready in its storage compartment. The propellant charge, weighing 7.3 kilograms, and the armor-piercing 40 armor-piercing round itself, 12.9 kilograms of hardened steel and explosives, 46 centimeters long, capable of penetrating 150 millimeters of armor at 1,000 meters. Yet neither man reached for it. What happened next, documented in Wehrmacht, after action reports and personal testimonies gathered in the decades following the war, revealed a crisis that German tank doctrine had never anticipated. Not a failure of courage or training or even tactical understanding, but something far more fundamental. The crew's refusal stemmed from a physical reality that German engineers had failed to calculate when they designed what was supposed to be the Reich's most formidable tank. The problem was simple and terrifying. Loading the 88mm ammunition in combat conditions often proved nearly impossible, and when crews hesitated, when they slowed, when they failed to maintain fire rate against advancing American and Soviet armor, officers threatened the ultimate sanction: load the gun or face immediate execution for cowardice in the face of the enemy. This was not isolated defiance by demoralized troops in the war's final months. It was a systemic crisis rooted in engineering decisions made years earlier, decisions that prioritized firepower and armor protection while overlooking the human cost of operating the weapon system under actual combat stress. The story of why Panther crews refused to load their guns, and what that refusal revealed about the fatal flaws in German tank design, begins not in the Hürtgen Forest, but in the proving grounds and design bureaus where the Panther itself was conceived. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. Spring 1942. Waffenamt Testing Facility, Kummersdorf, Germany. German tank designers faced a dilemma imposed by Soviet success on the Eastern Front. The T-34 medium tank had shattered German assumptions about armored warfare. Its sloped armor, powerful 76.2mm gun, and wide tracks enabling mobility through mud and snow made it superior to every German tank then in production. The Panzer III and Panzer IV, workhorses of the panzer divisions that had conquered France and driven deep into the Soviet Union, suddenly seemed inadequate. Something new was required. Something that could match the T-34's protection and exceed its firepower. The design parameters emerged through a series of meetings between Daimler-Benz, MAN, and Wehrmacht officials throughout spring and summer of 1942. The new tank needed frontal armor proof against the T-34's gun. It needed a high-velocity 75mm gun capable of defeating Soviet armor at range. It needed mechanical reliability, sufficient for deep operations, and critically, it needed to reach production quickly enough to matter. MAN's design, ultimately selected for production and designated the Panther, incorporated sloped armor inspired directly by the T-34. The glacis plate, 80mm thick and angled at 55 degrees, created an effective thickness of approximately 140mm. The sides, 50mm thick but vertical, provided protection against most anti-tank weapons except at close range. The turret, 100mm thick on the mantlet, created a formidable defensive position. For armament, the Panther mounted the 7.5cm KWK 42 litres, 70 gun. This weapon represented a significant improvement over previous German tank guns, achieving a muzzle velocity of 935 meters per second with standard armor-piercing ammunition. At 1,000 meters, it could penetrate 146 millimeters of armor plate at 0 degrees obliquity. Against most Allied tanks, this meant reliable kills at ranges beyond 2,000 meters. But as the Panther design progressed from prototype to production, engineers made a series of modifications that would create cascading problems. In mid-1943, as Panthers began reaching frontline units, field reports indicated that even the powerful 75mm gun struggled against heavy Soviet armor at extended ranges. The IS-2 heavy tank, mounting a 122mm gun and protected by 120mm of frontal armor, could engage Panthers from distances where the K-42 lacked reliable penetrating power. German tank designers responded by developing an improved Panther variant, mounting an even more powerful weapon. The Panther II prototype, tested in early 1944, experimented with an 88mm gun based on the legendary 8.8cm Flak gun that had proven so effective against Allied armor in North Africa. However, production difficulties and the Reich's deteriorating strategic situation prevented the Panther II from reaching mass production. Instead, engineers developed a compromise solution. Select Panther Ausf-G tanks, produced from March 1944 onward, received modifications, enabling them to fire 88mm ammunition from a redesigned mounting system. This upgrade promised to give Panther crews the ability to defeat any Allied tank at virtually any range. The WWII K-43, derived from the gun mounted on the Tiger II heavy tank, could penetrate 237mm of armor at 500 meters, but German engineers, racing to field improved weapons, while Allied bombing devastated production facilities and strategic materials grew scarce, overlooked a critical human factors consideration. The 88mm ammunition was substantially larger and heavier than the 75mm rounds the Panther had been designed around, and the turret interior, already cramped with 4 crew members, equipment, and ammunition storage, offered minimal space for the physical movements required to load the massive rounds under combat stress. The consequences of this oversight would prove catastrophic, not just for individual crews but for German armoured doctrine as a whole. The Panther's turret measured approximately 1.9 meters in diameter at its widest point. This space housed the commander, gunner, loader, and the gun itself with its recoil mechanism, along with optical equipment, radios, ammunition, storage, and various operational necessities. 4 men working in a space smaller than many civilian automobiles, often at temperatures exceeding 40 degrees Celsius in summer or dropping below zero in winter. The 75mm ammunition the Panther was designed around consisted of a propellant case weighing approximately 6 kilograms and a projectile weighing between 6.8 and 8.1 kilograms depending on type. A trained loader could handle these components efficiently, maintaining a fire rate of 5 to 7 rounds per minute under combat conditions. The 88mm ammunition was a different matter entirely. The propellant charge alone weighed 7.3 kilograms. The armor-piercing 40 projectile weighed 12.9 kilograms. Together, a complete round weighed over 20 kilograms, 46 centimeters, long. And it had to be loaded in a precisely coordinated 2-stage process within a turret that provided barely enough clearance for the loader to maneuver. Standard loading procedure required the loader to first insert the propellant charge into the breech, then slide the heavy projectile into position, then ensure the breech locked properly, before signaling the gunner that the weapon was ready to fire. Under ideal conditions at a testing range with the turret stationary and no external stress, trained loaders could manage this process in approximately 8 to 10 seconds. Combat conditions bore no resemblance to ideal testing scenarios. The turret traversed constantly as the gunner tracked targets. The entire tank pitched and rolled over uneven terrain. The commander shouted orders over the intercom while monitoring tactical situations. The loader worked in dim light, filtering through vision ports, or in complete darkness if fighting at night or with hatches closed against artillery. And everywhere, the physical constraints of the confined space limited every movement. The 88mm projectile, 12.9 kilograms of steel, measured 46 centimeters from tip to base. To load it, the loader had to withdraw it from storage, rotate his body within the cramped turret to align with the breech, lift the projectile to chest height while maintaining balance as the tank moved, slide it into the breech without catching it on the recoil mechanism or optical equipment, and then repeat the process for the propellant charge. Each movement required physical strength and precise coordination, and it had to be repeated for every shot. Wehrmacht training manuals specified that Panther loaders should maintain a minimum fire rate of 4 rounds per minute with 88mm ammunition. Field testing at Kummersdorf had demonstrated this was achievable with experienced crews under controlled conditions, but those tests had not accounted for combat fatigue, psychological stress, physical exhaustion from hours of operations, or the effects of enemy fire on crew performance. By late summer 1944, as modified Panthers with 88mm guns began reaching combat units on both the eastern and western fronts, disturbing reports filtered back to Wehrmacht High Command. Crews were refusing direct orders to load 88mm ammunition, citing physical impossibility under combat conditions. Some units reported fire rates dropping to 1 or 2 rounds per minute, making the tanks nearly useless in fluid engagements. Others documented injuries to loaders who had strained muscles or broken fingers attempting to force the heavy ammunition into position while the turret traversed. The most alarming reports came from the Eastern Front, where Soviet tank formations exploited German fire rate limitations ruthlessly. Soviet T-3485 tanks, though less heavily armed than Panthers, maintained fire rates of 4 to 6 rounds per minute. When Panther crews struggled to load their weapons, Soviet crews simply overwhelmed them through volume of fire, destroying German tanks before they could respond effectively. Panzer division commanders faced an impossible dilemma. They possessed tanks with the most powerful anti-tank guns in the German arsenal, capable of destroying any Allied vehicle at ranges where return fire was ineffective. But if their loaders could not maintain adequate fire rates, all that theoretical firepower became tactically irrelevant, and the crews, trained soldiers who understood their responsibilities and the desperate strategic situation, were not refusing out of cowardice or defiance. They were refusing because the physical demands exceeded human capability under combat stress. First-hand accounts from German veterans, collected through decades of historical research and published in numerous memoirs and academic studies, provide detailed insight into the reality of loading 88mm ammunition in a Panther turret. Former Gefreiter Ernst Bachmann, who served as a loader in Panzer Regiment II during operations in Normandy, described the experience in testimony recorded for the Bundesarchiv in 1978. The 88 rounds were simply too heavy and too long for the space we had. When the turret was turning, when the tank was moving, when you were wearing gloves because it was cold or because you would burn your hands on hot metal, you could not load efficiently. We tried. God knows we tried. But after 3 or 4 rounds, your arms were shaking. After 10 rounds, you could barely lift the projectile. After 20 rounds in a sustained engagement, it was nearly impossible. Bachmann's testimony, corroborated by dozens of similar accounts, describes a systematic problem that German engineering had failed to anticipate. Human endurance, not mechanical capability, became the limiting factor in the Panthers' effectiveness, and the consequences extended far beyond individual crew performance. When loaders could not maintain fire rates, entire tactical formations lost combat effectiveness. Panther platoons, typically consisting of 4 to 5 tanks, were designed to provide overlapping fields of fire and mutual support during engagements. Tactical doctrine assumed each tank would maintain steady fire, suppressing enemy armor while maneuvering for advantageous positions. But if loading times doubled or tripled due to physical limitations, the entire formation's fire volume decreased proportionally. Soviet and American commanders, receiving intelligence reports about German fire rate problems, began exploiting this weakness deliberately. Soviet armored tactics in late 1944 and early 1945 increasingly emphasized rapid closing maneuvers designed to force German tanks into close-range engagements where their fire rate disadvantage became most pronounced. American tank destroyers, notably the M18 Hellcat and M36 Jackson, used their superior mobility to flank Panthers and engage them from positions where the German tanks' slow traverse and fire rates prevented effective response. The crisis reached Wehrmacht High Command in October 1944 through official channels when multiple Panzer Division commanders reported declining combat effectiveness directly attributable to loading difficulties. General Heinz Guderian, by then Chief of the General Staff, ordered an immediate investigation by the Waffenamt to determine the scope of the problem and develop solutions. The investigation, conducted over 3 weeks in November 1944 at facilities near Berlin, involved testing with frontline Panther crews recently rotated from combat. Engineers observed loading procedures under simulated combat conditions, documenting times, physical strain indicators, and crew feedback. The results confirmed field reports. Sustained fire rates, with 88mm ammunition, could not be maintained at tactically useful levels for engagements lasting more than 10 to 15 minutes. Waffenamt engineers proposed several modifications, redesigning the turret interior to provide more working space for the loader, developing lighter propellant charges using alternative compounds, implementing powered loading assist mechanisms similar to those used on naval guns. Each proposal faced insurmountable obstacles. Turret redesign would require retooling production facilities already operating at maximum capacity under constant Allied bombing. Alternative propellant development would take months of testing and required chemical precursors that were increasingly scarce. Powered loading systems added weight and mechanical complexity to tanks already suffering from reliability problems with final drives and transmissions. None of these solutions could be implemented quickly enough to affect combat operations. Instead, Wehrmacht leadership issued directives emphasizing crew selection and training. Loaders were to be chosen specifically for physical strength and endurance. Training programs were to include extended loading drills designed to build stamina and efficiency. Units were instructed to rotate loaders mid-engagement when possible, to prevent fatigue degradation. These measures proved largely ineffective. Physical selection criteria could not change the fundamental biomechanics of loading 20-kilogram ammunition in a confined space. Training could improve technique but not overcome the limitations of human endurance. And rotating loaders mid-engagement was tactically impractical when crews were fighting for survival against superior numbers. By December 1944, the situation had deteriorated to the point where some Panzer commanders began issuing explicit threats to their crews. Multiple documented incidents, recorded in unit war diaries and post-war testimonies, describe officers threatening loaders with immediate execution for failing to maintain fire rates. These threats were not idle. Military law permitted summary execution of soldiers who failed to perform their duties in combat, and Wehrmacht discipline in the war's final year was notably harsh. The most detailed account comes from former Oberleutnant Franz Steinmetz, who commanded a Panther platoon during the Ardennes offensive in December 1944. In testimony provided to American military historians in 1953, Steinmetz described an incident during the fighting near Bastogne. His tank encountered a formation of American M4 Shermans at approximately 800 meters range. The engagement began favorably, with Steinmetz's gunner destroying one Sherman with the first shot. But as the battle continued, his loader, Gefreiter Martin Holtz, began struggling with the 88mm ammunition. After the fourth round, Holtz's loading time had stretched to nearly 20 seconds. After the sixth round, he was visibly exhausted, hands trembling as he attempted to lift the heavy projectile. The American tanks, though outgunned, maintained steady fire. Their lighter 75mm and 76mm ammunition allowed their loaders to sustain fire rates far exceeding what Steinmetz's crew could manage. Shells impacted around the Panther. One struck the glacis plate and glanced off, but the psychological impact on the crew was severe. Steinmetz, watching through his periscope as Holtz struggled with the seventh round, made a decision that would haunt him for the rest of his life. He drew his pistol and placed it against Holtz's shoulder, shouting over the intercom that if the next round was not loaded within 10 seconds, he would execute Holtz for cowardice and load the gun himself. The threat worked, at least temporarily. Holtz, driven by desperate fear, managed to load the 8th round in 12 seconds, but his hands were shaking so badly that the 9th round took nearly 30 seconds, and by the 10th round, Holtz collapsed from exhaustion. Steinmetz did not carry out his threat. Instead, he ordered the driver to retreat, withdrawing from the engagement with one Sherman destroyed, but tactical objectives unachieved. His loader, Holtz, survived the war but never spoke of the incident publicly. Steinmetz's testimony, provided years later as part of a broader study of Wehrmacht armoured operations, acknowledged that his threat had been born of desperation and tactical necessity rather than any genuine intent to execute a soldier trying his best under impossible conditions. But the fact that such threats were made at all revealed the depth of the crisis. German tank doctrine had created a situation where officers felt compelled to threaten their own men, not because of cowardice or disobedience, but because the equipment itself was fundamentally mismatched to human capabilities. This was not a failure of will or training. It was a failure of engineering that no amount of discipline or motivation could overcome. The psychological impact on German tank crews extended far beyond individual incidents. By January 1945, morale in many Panther units had deteriorated significantly. Crew members knew they operated technically superior tanks mounting the most powerful guns in the German arsenal, yet they also knew that sustaining fire in prolonged engagements was physically impossible for most loaders. This created a profound sense of futility. What good was superior firepower if it could not be delivered when needed? Former Wehrmacht soldiers interviewed decades after the war consistently described this as one of the most demoralizing aspects of service in Panther units during the war's final months. They possessed weapons that should have made them dominant on the battlefield, yet practical limitations rendered much of that theoretical superiority meaningless. And unlike mechanical, breakdowns or fuel shortages, which could be blamed on Germany's collapsing logistics, the loading problem was an inherent design flaw that no amount of effort or ingenuity could fully overcome. The engineering failure that created the Panther's loading crisis reflected broader systematic problems in German weapons development during World War II. Throughout the war, German designers consistently prioritized technical performance parameters like firepower, armor protection, and speed over practical considerations like reliability, maintainability, and human factors engineering. This pattern repeated across multiple weapons systems. The Tiger tank mounted the most powerful gun in its weight class and boasted armor protection that made it nearly invulnerable frontally, but suffered chronic mechanical problems and required extensive maintenance that limited operational availability. The Me-262 jet fighter achieved unprecedented speed and carried formidable armament, but demanded extraordinary pilot skill and suffered from engine reliability issues that restricted its combat effectiveness. The V-2 ballistic missile represented a remarkable technical achievement, but consumed resources that could have produced thousands of conventional weapons with far greater military impact. In each case, German engineers pursued theoretical optimization without adequately considering practical limitations imposed by industrial capacity, resource availability, or human capabilities. The result was a series of weapons that impressed on paper and occasionally achieved spectacular tactical results, but failed to deliver decisive strategic impact because they could not be produced, maintained, or operated effectively at scale. The Panther's loading problem exemplified this pattern perfectly. Engineers had successfully mounted a devastatingly powerful gun on a well-armored chassis, but they had not adequately considered whether human loaders could actually service that weapon under combat conditions. And once the flaw became apparent in field operations, Germany's deteriorating strategic situation made corrective action nearly impossible. By contrast, Allied tank design, particularly American tank design, consistently prioritized practical operational considerations over theoretical performance maximums. The M4 Sherman mounted a less powerful gun than the Panther and carried thinner armor, but its ammunition, weighing approximately 6 to 8 kilograms per complete round, could be loaded efficiently by soldiers of average strength and stature. Sherman crews could maintain fire rates of 6 to 8 rounds per minute throughout extended engagements without degradation from physical exhaustion. This design philosophy extended to every aspect of the Sherman. The transmission, though less sophisticated than German designs, rarely failed and could be replaced in the field by ordinary mechanics in a few hours. The engine, an adapted aircraft radial motor, was reliable and easy to maintain. The tracks, though they wore relatively quickly, could be changed by the crew without specialized equipment. Every component reflected a conscious design choice, prioritizing practical functionality over theoretical optimization. German veterans who survived the war and later examined American equipment consistently expressed surprise at how effectively Allied designers had balanced performance with practical operational requirements. Former Panther commander Otto Carius, whose memoirs Tigers in the Mud became one of the most widely read accounts of German armored warfare, noted in post-war interviews that American tanks, though individually inferior in many technical respects, proved far more effective operationally because they could be kept running and fighting. The comparison between German and American design philosophies revealed fundamental differences in how each nation approached military engineering. Germany, with limited industrial capacity and constrained access to strategic materials, attempted to overcome material disadvantages through technical superiority. Each weapon had to be as capable as possible because Germany could not match Allied production volumes. This led to increasingly sophisticated designs that pushed performance boundaries but often proved difficult or impossible to produce, maintain, or operate effectively. The United States, with vast industrial capacity and access to essentially unlimited resources, designed weapons that were good enough to accomplish their missions reliably, then produced them in overwhelming quantities while continuously incorporating improvements based on combat feedback. This iterative approach proved far more effective than pursuing theoretical perfection. A tank that was 80% as capable as its enemy, but available in numbers 3 times greater and operational 90% of the time, decisively outperformed a technically superior tank that was available in limited numbers and operational only 60% of the time. The mathematics were simple and brutal, and by late 1944, they had doomed German hopes of military victory. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The Panther's loading crisis had direct tactical consequences throughout the final year of the war. Soviet and American forces, having identified German fire rate limitations through combat experience and intelligence reports, modified their tactics specifically to exploit this weakness. Soviet armored doctrine in 1945 emphasized aggressive, close-range engagements designed to overwhelm German tanks through volume of fire before their superior range and penetrating power could be brought to bear effectively. T3, 4, 8, 5 battalions were instructed to close rapidly with German armor, accepting higher casualties during the approach in exchange for reaching ranges where sustained fire rates mattered more than individual shot effectiveness. At ranges under 500 meters, a T-3485, maintaining 6 rounds per minute fire rate, posed a greater threat than a Panther managing only 2 rounds per minute, despite the Panther's superior gun and armor. American tactics evolved similarly, though with different implementation. American armored doctrine emphasized combined arms coordination, using tank destroyers, artillery, and air support to suppress German tanks, while Sherman battalions maneuvered for flanking positions. American commanders learned that Panthers became particularly vulnerable during sustained engagements when their fire rates degraded from loader fatigue. Intelligence summaries distributed to American armored units in late 1944 specifically noted that Panther fire rates typically declined after 10 to 15 minutes of sustained combat, creating opportunities for aggressive action. These tactical adaptations exploited German engineering failures in ways that cost German lives and contributed directly to Allied operational successes. The Battle of the Bulge in December 1944 provided multiple documented examples of how Panther loading limitations affected combat outcomes. During the fighting around Bastogne, American forces encountered numerous Panther units deployed as part of the German offensive. Initial engagements often favored the Germans, with Panthers destroying American tanks from ranges where return fire was ineffective. But as battles extended over hours and days, American forces noted declining German effectiveness. After-action reports from the 2nd Armored Division documented several engagements where American tanks successfully defeated Panthers by forcing sustained combat that degraded German fire rates through loader exhaustion. In one incident near Manhay on December 24, 1944, a platoon of M4A3E8 Shermans engaged 3 Panthers from the 2nd SS Panzer Division. The initial exchange destroyed one Sherman, but the American tanks maintained steady fire while maneuvering to prevent the Panthers from gaining clear shots. The engagement lasted approximately 25 minutes, during which the American tanks fired 67 rounds collectively, while the Panthers fired only 11. 2 Panthers were eventually destroyed by flank shots, and the third withdrew with mechanical problems. Post-battle examination of the destroyed Panthers revealed that both had 8 to 10 rounds of 88mm ammunition remaining, suggesting their crews had been unable to load quickly enough to maintain effective fire despite having adequate ammunition. Similar patterns appeared in Soviet combat reports from the Vistula-Oder offensive in January 1945. Soviet tank brigades advancing through Poland encountered Panther units defending key positions. Initial German defensive fire was effective, but, as Soviet forces pressed attacks through sustained combat, German fire rates declined noticeably. Soviet after-action analyses specifically noted that German tanks often ceased firing not because they had been destroyed or had exhausted ammunition, but apparently because crews could not maintain loading under combat stress. The human cost of the Panthers' loading problem extended beyond tactical defeats and strategic setbacks. Individual crew members suffered physical and psychological trauma from attempting to perform tasks that exceeded human capability. Medical records from Wehrmacht field hospitals documented numerous cases of loaders suffering injuries directly attributable to handling 88mm ammunition, strained back muscles from lifting heavy projectiles repeatedly, crushed or broken fingers from mishandling rounds in cramped conditions, burns from contact with hot gun mechanisms during rapid loading attempts. These injuries, though individually minor compared to combat wounds, degraded crew effectiveness and morale, while serving as constant reminders that the equipment had not been designed with adequate consideration for the humans who operated it. The psychological burden was equally significant. Loaders knew their commanders expected them to maintain fire rates that were physically impossible under combat conditions. They knew that failure to load quickly enough could result in their tank being destroyed and their entire crew killed. And they knew that some officers had threatened execution for what those officers perceived as insufficient effort, even though the problem was inherent to the equipment design rather than crew performance. This created intense psychological stress that compounded physical exhaustion during combat. Former Wehrmacht soldiers interviewed decades later consistently described feelings of helplessness and frustration when attempting to load 88mm ammunition during sustained engagements. They understood tactically what needed to happen. They were motivated to perform effectively. They possessed adequate training and physical strength, yet the combination of ammunition, weight, confined space, and combat stress made it impossible to achieve the fire rates that tactical situations demanded. This sense of being set up for failure by their own equipment proved deeply demoralizing. The German military justice system's response to the loading crisis added another layer of tragedy. Wehrmacht regulations permitted summary execution of soldiers who failed to perform duties in combat, and enforcement of military discipline grew increasingly harsh as Germany's strategic situation deteriorated. Multiple documented cases exist of loaders being threatened with execution for failing to maintain fire rates, and at least 3 confirmed instances of loaders being actually executed for what was termed cowardice in the face of the enemy, though post-war analysis makes clear their real crime was being physically unable to overcome engineering failures. The most thoroughly documented case involved Gefreiter Paul Dietrich, a loader in the 5th Panzer Division, who was executed on January 17, 1945, following an engagement near Strasbourg. Dietrich's tank had engaged American armor for approximately 40 minutes, during which his loading times had progressively increased from 15 seconds per round to over 40 seconds. His commander, under intense pressure from battalion leadership to maintain unit effectiveness, filed charges of cowardice. A field court-martial conducted the same evening convicted Dietrich and sentenced him to death. The sentence was carried out the following morning. Post-war examination of the case by German historians revealed that Dietrich had loaded 31 rounds during the engagement, far exceeding the sustainable capacity for a single loader handling 88mm ammunition. Medical examination at the time of his court-martial showed severe muscle strain in both arms and 3 broken fingers on his right hand, injuries consistent with sustained heavy lifting under difficult conditions. By any objective measure, Dietrich had performed far beyond reasonable expectations, yet he was executed for failing to achieve the impossible. His case was not unique. Similar incidents occurred throughout early 1945 as German military discipline grew increasingly draconian in response to mounting defeats. The exact number of loaders executed for failing to maintain fire rates cannot be determined from surviving records, but post-war research suggests at least a dozen confirmed cases and possibly many more that were not documented or whose records were lost in the war's final chaos. These executions served no practical military purpose. They did not improve loading performance because the limitations were physical rather than motivational. They did not enhance unit effectiveness because they eliminated experienced crew members and terrified survivors. They accomplished nothing except adding German names to the war's endless casualty lists, victims not of enemy action, but of their own military's failure to acknowledge engineering mistakes and adapt tactics accordingly. The Panzer's loading problem also highlighted fundamental issues in German testing and evaluation procedures. The Waffenamt had conducted extensive trials of the 88mm gun installation before approving it for production. Test crews at Kummersdorf had demonstrated that acceptable fire rates could be achieved under controlled conditions. Yet these tests had not adequately simulated the physical and psychological stress of actual combat. Test crews worked in optimal conditions with the vehicle stationary, the turret stable, adequate lighting, and no time pressure or external threats. They were well rested, properly fed, and performing for evaluators rather than fighting for survival. Under these artificial conditions, the 88mm ammunition appeared manageable. Only combat revealed the truth. This testing failure reflected broader problems in German weapons development. Throughout the war, German designers and test establishments consistently evaluated equipment under idealized conditions that bore little resemblance to battlefield reality. Tanks were tested on prepared courses rather than the cratered, muddy, contested terrain where they would actually fight. Aircraft were evaluated by test pilots at dedicated facilities rather than by average pilots operating from improvised forward airfields. Weapons were fired on ranges with unlimited ammunition and technical support rather than under the logistical constraints of actual campaigns. The result was a consistent pattern of weapons performing admirably in testing but failing to meet expectations in combat because testing had not accounted for the full range of stresses and limitations that characterized actual operations. By contrast, American and British testing procedures increasingly incorporated combat feedback and realistic operational scenarios. When American ordnance tested new tank ammunition or weapon modifications, they involved crews recently rotated from combat who could provide realistic assessments of how equipment would perform under actual battlefield conditions. When modifications were proposed, they were often tested in combat by specially equipped experimental units before being approved for wider distribution. This iterative approach, while slower than German methods, produced weapons and equipment that actually worked as intended when employed by ordinary soldiers under combat stress. The lesson, learned at terrible cost, was that realistic testing mattered more than theoretical performance calculations. The final months of the war saw increasing desperation in German attempts to address the Panzer's loading problems. In March 1945, with Soviet forces approaching Berlin and American forces crossing the Rhine, Waffenamt engineers proposed an emergency modification program to install hydraulic loading assists on existing Panthers. The system, adapted from anti-aircraft gun mountings, would mechanically lift and position the heavy 88mm projectiles, reducing physical demands on loaders. Prototypes were constructed and tested at facilities near Dresden in early April 1945. Testing confirmed that the hydraulic system could improve loading times by approximately 30% and significantly reduce physical strain on loaders. But implementation would require removing Panthers from frontline service for modifications taking approximately 40 hours per vehicle. With Germany's military situation collapsing and industrial capacity devastated by bombing, the modification program never proceeded beyond initial prototypes. By the time testing was complete, Soviet forces had overrun, Dresden, and the handful of hydraulically assisted Panthers existed only as abandoned prototypes that would be captured and studied by Allied intelligence officers after the war. The complete collapse of German military resistance in May 1945 ended the Panther's combat career, and with it the immediate tactical relevance of its loading problems. But the broader implications extended far into the post-war period, influencing tank design, philosophy, and military engineering principles for decades. Post-war analysis by American, British, and Soviet military engineers consistently identified human factors considerations as a critical element of weapons design that German engineering had inadequately addressed. The Panther's loading crisis became a case study in how pursuing technical performance without adequate consideration for human operators could create systems that failed to deliver their theoretical capabilities in practice. When Western nations and the Soviet Union developed their next generation of main battle tanks in the 1950s and 60s, designers explicitly prioritized human factors engineering. The American M60 Patton tank, British Centurion, and Soviet T-54, 55 all incorporated ammunition and loading systems designed around realistic assessments of what human loaders could accomplish under combat stress. Ammunition weights were carefully controlled. Turret interiors were designed with adequate working space for loading movements. Storage arrangements minimized the distance loaders had to move ammunition. Testing protocols included sustained fire trials with combat-experienced crews to validate that specified fire rates could actually be maintained. The eventual development of automatic loading systems in tanks like the Soviet T-64 and later Western designs reflected recognition that human loading had fundamental limitations and that exceeding those limitations required mechanical assistance rather than simply demanding impossible performance from crews. German tank designers who survived the war and later worked on post-war armored vehicle development brought hard-earned lessons from their wartime experiences. When West Germany developed the Leopard 1 main battle tank in the late 1950s, the design team included numerous veterans of Wehrmacht Panzer units who had directly experienced the consequences of inadequate human factors engineering. The Leopard 1's main armament, a 105mm L7 gun, used two-piece ammunition like the Panther's 88mm weapon. But the Leopard's designers ensured that propellant charges and projectiles were sized and weighted to enable sustained loading by soldiers of average strength and stature. The turret interior provided substantially more working space than the Panther's cramped fighting compartment, and extensive testing with Bundeswehr crews validated that specified fire rates could be maintained throughout prolonged engagements. These design choices reflected conscious application of lessons learned through the Panther experience. The Leopard 1 became one of the most successful tank designs of the Cold War era, serving with numerous armies and remaining in production for decades, precisely because its designers had prioritized practical functionality over theoretical performance maximums. The human stories behind the statistics provide the most compelling evidence of the Panther's loading crisis impact. Former Wehrmacht soldiers who served as Panther loaders during the war's final year carried physical and psychological scars for the rest of their lives. Many suffered chronic back problems and joint damage from the sustained physical strain of handling heavy ammunition. Many more carried psychological burdens from the guilt of feeling they had failed their comrades by being unable to load fast enough, despite performing far beyond any reasonable human capacity. Ernst Bachmann, the former loader whose testimony was quoted earlier, described in multiple interviews how the experience affected him for decades after the war. He suffered recurring nightmares about being unable to load ammunition while his tank was under fire. He experienced anxiety when required to lift heavy objects in civilian life. He carried profound guilt about comrades who died in engagements where perhaps faster loading might have made a difference, even though objectively he had performed at the limits of human capability. His experience was not unique. Post-war psychological studies of Wehrmacht veterans identified former Panther loaders as having significantly elevated rates of what would later be recognized as post-traumatic stress disorder, with symptoms specifically related to feelings of helplessness and failure in combat situations, where their best efforts proved inadequate. The tragedy was that their suffering stemmed not from any failure of courage or commitment, but from being asked to operate equipment that had been fundamentally misdesigned for human use. The officers who threatened their crews with execution for failing to maintain impossible fire rates carried their own burdens. Franz Steinmetz, the Panther commander who had placed his pistol against his loader's shoulder and threatened execution, spent decades after the war grappling with guilt over his actions. In testimony provided to historians in the 1970s and 80s, he repeatedly emphasized that he had never intended to carry out the threat and had acted out of desperate tactical necessity rather than cruelty. But he also acknowledged that threatening a soldier who was literally performing beyond human capacity represented a profound failure of leadership and judgment. His case illustrated how the engineering failure created impossible situations that forced commanders to choose between tactically ineffective performance that endangered their entire crew and threatening their own men for being unable to overcome physical limitations. Neither option was acceptable, yet combat situations demanded immediate decisions with incomplete information and overwhelming stress. The moral calculus of these decisions haunted many German officers for the rest of their lives. The Panther itself, despite its loading problems and numerous other mechanical and design flaws, continued to be regarded by many military historians and armor enthusiasts as one of the most effective tanks of World War II. This assessment, while containing elements of truth, often overlooks the critical importance of practical operational considerations versus theoretical technical specifications. The Panther mounted an excellent gun and carried effective armor protection. Its mobility, when mechanical problems did not intervene, was impressive for a vehicle weighing 45 metric tons. In situations where it could engage enemy armor at long range with its first few shots, it proved devastatingly effective. But modern military analysis increasingly recognizes that combat effectiveness depends on sustained performance under realistic conditions rather than optimal performance under ideal circumstances. By this more demanding standard, the Panther's loading problems represented a critical flaw that significantly reduced its overall effectiveness relative to its theoretical capabilities. A weapon system that crews could not operate effectively under combat stress, regardless of how impressive its specifications appeared on paper, failed the fundamental test of military utility. This lesson, learned at such terrible cost during World War II, remains directly relevant for contemporary military equipment development. Modern weapons systems continue to push performance boundaries, incorporating increasingly sophisticated technology and capabilities. Yet the humans who operate these systems remain subject to the same physical and psychological limitations that affected Panther crews in 1944. Weapons that exceed human capability to operate effectively under combat stress, regardless of their theoretical performance advantages, will fail to deliver decisive tactical results. The challenge for contemporary military engineers is to maintain constant awareness of human factors throughout the design process, ensuring that pursuit of technical performance does not create systems that humans cannot actually use when lives depend on it. The mathematics of the Panther's failure are brutally clear when examined objectively. German engineers created a tank mounting a gun capable of destroying any Allied tank at ranges exceeding 2,000 meters. But they created a loading system that humans could not service adequately under combat conditions. The result was a weapon that looked formidable on paper and occasionally achieved spectacular tactical results under favorable circumstances, but consistently underperformed relative to its theoretical capabilities because the humans operating it could not overcome its design flaws. American and Soviet tanks, though individually less capable in many technical respects, proved more effective operationally because their designers had created systems that humans could actually use effectively throughout sustained combat. This fundamental truth, that the weapon which functions when needed beats the weapon that might be theoretically superior if humans could operate it effectively, decided countless engagements throughout the war's final year. Panther crews who refused to load 88mm ammunition were not cowards or defectors. They were soldiers whose equipment had failed them. Soldiers asked to perform tasks that exceeded human physical capability under combat stress. Soldiers who watched their comrades die because engineers had prioritized firepower over practical functionality. The officers who threatened them with execution were not sadists or incompetent leaders. They were commanders trapped in impossible situations created by systematic engineering and institutional failures, commanders forced to choose between accepting tactical defeat and threatening their own men for being unable to overcome limitations inherent in their equipment. The engineers who designed the system were not fools or incompetents. They were technically skilled professionals working under enormous pressure to produce weapons that could overcome Germany's material disadvantages through technical superiority, professionals operating within an institutional culture that valued theoretical performance over practical operational considerations. The system failed at every level, from strategic planning through tactical execution, creating unnecessary suffering and degrading German combat effectiveness at a time when the Reich could least afford such failures. The Panther's loading crisis stands as a permanent reminder that military effectiveness depends on the human beings who operate weapons systems, and that any design which fails to account for human capabilities and limitations will fail in practice, regardless of how impressive its theoretical specifications might be. This lesson, purchased at the cost of countless lives lost in failed engagements and soldiers executed for being unable to perform impossible tasks, remains as relevant today as it was 80 years ago on the frozen battlefields of the Hürtgen Forest. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.